Intelligence helps additive manufacturing teams to apply advanced machine learning methods in order to optimize their AM processes. The intelligence software, Alchemite, is uniquely strong at extracting value from the sparse, noisy data that is typical of AM projects. It enables users to identify and understand vital property-process relationships, ensure more reliable, repeatable AM processes, reduce the amount of experiment needed to get to a result by up to 80%, and accelerate the delivery of AM projects. Intelligence is an innovative software company working actively with leaders in the materials, process, formulations, and additive manufacturing spaces. With technology originally validated in a project at Rolls-Royce, we've recently published case studies with organisations including, among others, GKN Aerospace, the AMRC and Boeing, and Welding Alloys Group. Intelligence is a spin-out from the physics department in the University of Cambridge. Co-founder and CTO Dr. Gareth Conduit explains.
Our research group has developed a deep learning methodology that, unlike conventional methods, can learn from sparse and noisy data. This means that the methodology is particularly well suited to handling real-life experimental data. Our deep learning methodology can identify the optimal processing variables and also perform virtual experiments, thereby reducing the need to perform expensive and time-consuming prototypes.
Intelligence was founded to implement and take forward these methods as commercial software. Based in Cambridge, our team of computer scientists, physicists, data scientists, and materials specialists is driving forward the development and use of the Alchemite machine learning platform in close collaboration with industrial customers. Additive manufacturing has become a key focus area in recent years. Over to Intelligence CEO Ben Pellegrini to learn more.
Hi, I'm Ben Pellegrini, CEO at Intelligence, and today I'd like to talk to you about how we're helping additive manufacturing teams optimize their processes. We all know that AM has huge transformational potential to deliver lighter, stronger parts and novel product capabilities. But we also all know that ensuring repeatable AM processes is a difficult challenge. AM builds are highly sensitive to material properties, process parameters, and processing conditions. AM teams want to control these factors for the best, most reliable performance, but this is a complex optimization problem. Getting it right requires many builds and a battery of tests on each. Experimental costs for a single project can run to hundreds of thousands of dollars, and the process is time-consuming. Simulation helps, but simulation itself requires expert input, time and resources. And correlations between simulated and experimental results are not always obvious. Ideally, AM teams want to make sure that they are making the best possible use of all the data available to them, from past projects, current builds, and testing and simulation. Within this data are clues to vital property-process relationships, or information that can help to focus the next round of testing and simulation more effectively. Machine learning should be a tool to crack this data challenge, but there are problems in using it. The real experimental data that you have from AM projects is often sparse. It does not record every value for every possible property or process parameter, and it is usually noisy, subject to experimental error or inherent variability. Sometimes there is too little data, for example on material properties. You can fill in gaps by learning from related data, for example from other projects or third-party providers. But combining data sources in this way again creates sparse data sets. Conventional machine learning methods fail because you cannot train their models with sparse, noisy data. Then there is implementation. Expert data scientists waste time massaging data and writing code to overcome these data challenges, while AM domain experts are put off by the complexities of setting up models, often needing coding or scripting skills. That's where Alchemite comes in. It's easy to use software that enables data scientists and AM specialists alike to get started fast applying machine learning. It takes AM data from builds, tests or simulation and applies the Alchemite algorithms to immediately generate useful machine learning models, even when data is sparse and noisy. You can then apply those models to find out which process parameters are really controlling your target properties. Recommend which experiments to do next in order to refine your model, dramatically reducing the number of builds and tests needed to understand your process. Identify optimal process parameters and conditions. Get a quantitative understanding of uncertainties to focus on the most reliable routes. And predict the likely performance of candidate processes, avoiding costly experiments that are likely to fail. The best way to understand Alchemite is to see it in action. Let's join my colleague, Dr. Tom Whitehead, Head of Machine Learning at Intelligence.
To get started with Alchemite, we get going with our data in a spreadsheet format. In this spreadsheet, each row corresponds to a historic additive manufacturing build that we've run in the past, and then each column corresponds to some feature of that build. So the first few columns here are properties of the powder that we used. And then we have 3 columns on the additive manufacturing process that was used. The final 3 columns give experimental measurements that were carried out on the resulting build material. We can see that the experimental data is sparse. There are gaps in it. This could come perhaps if the different experimental measurements have come from different projects, where different projects were interested in different experimental endpoints. Then, when we combine the data together, they don't overlap 100% fully, and we end up with some gaps. Regardless of where the gaps came from, once we've got this data in a spreadsheet format and uploaded it into Alchemite, Alchemite automatically trains a machine learning model that captures all of the relationships in this data. And then, with the click of a button, we can fill in those gaps, work out what would have been measured in those experiments had they been run. We can also use Alchemite to make predictions for new materials and new processes that haven't been tried before. On this screen, we can specify a powder and a set of processing variables that we're interested in testing out. We click Predict and come up with predictions for the tensile strength and the elongation and the density, all of those output experimental measurements. This can be useful for testing out ideas for new powders, for new processes, for both at the same time, and quickly triaging the results. We can also ask the same question in reverse. So instead of giving Alchemite the powder and the processing parameters and asking it what the properties will be, we can give it the properties that we need to achieve for our project to be successful, and ask Alchemite what powder and what processing variables should I use to get there. For example, maybe for our project we need a high tensile strength and a low elongation. We could prioritize these relative to each other. Let's say for this particular example, tensile strength is more important than the elongation. And we can put constraints on the inputs that Alchemite is allowed to explore, on the powders or the processing variables that it's allowed to look through. Again, with a click of a button, Alchemite goes away and finds a material that's most likely to achieve these goals. In this case, it thinks there's about an 85% chance that this material will achieve that goal we asked for. We can dive into this result in a bit more detail on the Analyze tab. Clicking through to this graph, we can look at how the elongation varies as a function of the laser power used in the build. The red point here is the optimization that Alchemite has come up with. And now we can look at this graph and extract knowledge from it to build our own understanding, our intuition, our material science knowledge of how this system behaves, extracting information from the machine learning model. Alchemat has a variety of other tools that enable you to extract information about how the model is built. For example, on the analytics page, we have an importance matrix, which shows which inputs variables contributed most strongly to the predictions of each output. Here we can see that the laser power and the hatch scan speed, so the processing parameters, had the biggest impact on the resulting properties. This sort of insight and many others are available through the Alchemat Analytics platform. If you'd like to hear more about any of the features in the platform, please get in contact with us.
Alchemat is now proven software, having been successfully applied to projects in additive manufacturing and materials design. One of its first applications was in the design of an aerospace alloy with Rolls-Royce. Here, Alchemat methods were used to identify a new nickel-based superalloy that could simultaneously fulfill 11 different physical criteria, exceeding the performance of existing commercially available alloys. In collaboration with GKN Aerospace, the software was applied to an additive manufacturing problem, finding a titanium alloy composition that maximized thermal conductivity while retaining the required mechanical properties. The goal was to improve design of additively manufactured heat exchangers. Another project was featured in a recent webinar with the UK's Advanced Manufacturing Research Centre. Project MEDAL is a collaboration between Intelligence, the AMRC and Boeing, supported by the UK National Aerospace Technology Exploitation Programme, NATEP. Alchemat is being used to accelerate the experimental program associated with designing new AM processes. The graph on the screen shows some results discussed during the webinar. Here, Alchemat is used for design of experiments, providing guidance on which builds and tests should be done next in order to most efficiently explore possible processing parameters. Alchemat is compared to other design of experiments methods. Experimental programs designed with Alchemat are found to deliver results significantly faster than those designed with other methods. The scale is logarithmic, so in some cases the result was an order of magnitude fewer experiments. Applied to a real experimental program for an AM project, such gains can represent millions of dollars of direct experimental cost savings and months of project time.
Hopefully you've seen from this short presentation how Alchemat's deep learning technology can really accelerate additive manufacturing processes. We at Intelligence enjoy working collaboratively with our industrial partners, so please do get in touch if you'd like to learn more. Please visit our website and contact us to learn more about how Alchemat can enable data-driven additive manufacturing. As we have seen, this can allow you to identify and understand vital property-process relationships, develop more reliable, repeatable AM processes, reduce the amount of experiments needed to get a result by up to 80%, and really accelerate the delivery of your AM projects.